Hello everyone, today I am going to deliver another lecture, structural analysis by deductive stiffness method for 2D beam and frame. Okay, so let's start. Here is some content. So let's see the stiffness matrix of two-dimensional frame in local axis, and then I will cover the transformation of stiffness matrix from local to global axis, and then assembly of the stiffness matrix load factor for a 2D frame, and then fourth stiffness matrix for 2D frame neglecting axial deformation, and then finally I will see the some practice problem of stiffness matrix from beam and frame. Okay, so before I'm starting to lecture, so let's see why we should know the stiffness matrix, because we can analyze the determinate structure as well as the indeterminate structure. So we can, if the structure is applied load, then we can also use for this, and we can also found the deflection and rotation also. Okay, there are lots of element we can analyze using this method. So such as we can see the 2D truss, 2D frame, 2D beams and grid, and consequently we can use 3D truss, 3D frame and gates. So not only this, but also we can use this for a non-linear problem. So we can see the geometry non-linearity from beam and frame, and plastic analysis from beam and frame, and direct stiffness method for structural dynamics. Okay, so our today's topics is two-dimensional 2D frame. So let's see. So these are the our main focus. So structural analysis by direct stiffness method for 2D frame net, and here is a content. So let's start, and we'll see the stiffness matrix from two-dimensional frame in local axis. So if we go to the here, here we can see a beam is shown here, and point 1 is left side, we can call A, and right side is point B, and we can use three phenomena. One is X, which is axial load from left to right, another is vertical load, which is YB, and another one is moment. So in the same thing is happened in point B. So we can see here, point A. So we have been seen the point A. So as we have used the one axial load. Here the axial load we have been used from left to right. Sorry. So left to right. So 1 unit we have been used. This is the SX. So we can call it SX. In the same thing for point A, we just using a vertical displacement, which is SA. If we give the SA, in the opposite direction must be S2. So we have been giving SO in upward in the for equilibrium purpose in the opposite support. So SA will be here and S2 will be in the opposite direction. So what is the meaning of SA? So if we go to the if we see here, this is the some basic formula must be memorized. There is no other option. So SX is we have been seeing here, the SX is the axial load. So SX will be EL by L, but S1 12 bi by L cube and S2 6 EI by L square, S3 4EI by L, and S4 2EI by L. So we have been seen here, this is the SA and S2. So that means we have been used 12EI by L in here, and S2 is opposite direction, which is 6EI by L square. And the same thing is happen as S1 12EI by L cube, and opposite direction S2, which is 6EI by L square. Okay, let's let solve the three. As we have been first we have been use the axial deformation, and then we have been use the vertical deformation is here. Now we can use the moment or rotation in the same point A. So let's see that we have been seeing the in the taking on one rotation in point A. We have been taking it, and the member will be rotating, goes down. When the render is rotating goes down, then this sagging point, counter sagging point will be S3. The S3 and S2 will be opposite direction, as we have been seeing S1 S2 is opposite direction. But keep in mind that so S3 is here, but it will be S4. On the other hand, we have been seeing the S2 and S2 in the opposite side, is so S2 is same. But in the rotation cases, S4 is S3 is for the rotation point, but S4 is the opposite point. What is the value of S3 and S4? So if we see here, S3 is 4EI by L, and S4 equal to 2EL by L. And the same thing, S1 is 12, and S2 is 6. So it is just half. If we want to memorize this, the 12 is half is 6, and 4 half is 2. Okay. So now point for B, this is the point B. So if we calculate for point B, this is the B. So now first of all we are applying the axial force. This is the axial force SA, and the vertical YB. So now we are going to the vertical. We have been taking the vertical S1 in upward. So in S2 will be opposite direction. In the same thing, S1 is downward, and S2 will be opposite direction of S1. Now you can see the rotation or torsion. We are taking the rotation anti-clockwise, as well as anti-clockwise. So if we member is rotating here, then the sagging point is S3, and the S2 will be opposite, and S4 in the opposite point. Here is S4, and S2 will be opposite at the same point. The value is we have been shown here. S1 is 12EI by L, S2 is 6EI by L square, S3 equal to 4EI by L, and S2 equal to 2EI by L. This value is remain same. You must be memorized. Okay. Okay. These are the final. These are the we can see stiffness matrix two-dimensional frame in the local axis. Okay, now we can see here the equilibrium equation. We are taking 1 2 3 4 5 6. We have been seeing here. This is the 1 2 3 4 5 6, and 7 is here. So XA, we are taking the moment of XA, and we have been found SAX, and S2 is there is no axial load. S3 is no axial load. X4 is axial load is appeared is here, but S5 is no axial load. X6 also no axial load. M6 and we have been assembled these equations. Okay. So the same thing, stiffness matrix for two-dimensional frame and local axis we have been shown here. We have been already seen here. Consider the frame may be subjected to from that some forces, which is XA, YA, MB, and XB, YB, and MB at the joint A and B. This is the joint A, and this is the joint B. Assume that the length of the member is, we can see here the L, and the modulus of elasticity is S, and cross-sectional area is A. In the moment of inertia, we can see I axis, the axial stiffness Sx, the load produced by EI, and assume S1 the axial shear stiffness 12 EI by L cube, and S2 6 EI by L cube. Okay, this is the formula we must be memorized. And S3 is flexible stiffness 4 EI by L, and S4 equal to 2 EI by 2 EI by L. This is the another formula we can see. Okay, so if in the displacement and rotation point A and B, then we can found this type of phenomena. So we have already shown this phenomena and founding this equation. After founding equation, then we have been assembled this here as we have been shown here. Okay, and now we are going to the next topic, which is transformation of stiffness matrix from local to global. So here is the transformation stiffness matrix from local to global. The member of matrix found in local axis system can be transformed into the global axis system by considering angle they make with horizontal. It's always horizontal. So it is keep in mind by any means. Okay, the local displacement or rotation and the global displacement rotation are relatively following the equation. So we have been seen in there is the equation omega UA into cos theta. This is the UA. G means global. So UA is global, is cos theta, and the UA G global in sin theta in the same VA G. This is the VAG sin theta. So always is horizontal, and this is also vertical. Cos theta is we can say this is the horizontal, and VAG sin theta is we can say vertical. Okay, after in the consequently for UV we've been found minus UG sin theta and plus UV sin theta, and forming these equations. Okay, and now we are go to the assemble of the stiffness matrix load vector to 2D frame. So let's go. Here is the assembly of stiffness matrix load vector of 2D frame. So we have been seen here the very complex situation. Now we can see here the assemble the global stiffness matrix writing the global vector shown in below. Also boundary condition we have been shown here, EI and ES also. Okay, so let's solve it. How to solve this problem? Okay, let's see. Here is the global stiffness matrix written in global vector of the frame shown below, and also write the boundary condition. So EAI are the constant for all member. Okay, so we've been founding EAIL. So it is given. So SXX, as we can remind you that this was our formula, SX EI by L. So don't ask how we will get this is the formula, EI by L, and found here. And S1 12 EI by L cube, S2 6 EL by L square, S3 6 square, S4 2L by S square. Okay, and these are the given here. So we have been seen member lots of member AB, BC, where the AB is 0 0 as the horizontal, theta will be with respect to horizontal, and for member BC, this is the vertical member. For vertical member, the theta will be 90 degree, and C equal to 0 in sin 90. Okay, so after founding for fixed in moment AB, we have been founding PL by 4 as a point load. Here is the point load. For usual load, PL by L square, PL square by or WL square by 12, and founding this below. After founding this below, we can formulate this formula and funding here. After funding here, just we can cross up, just as there is no rotation is allowed, as we've been shown here 1 2 3. 1 is axial, 2 is vertical, and 3 is rotation. The same thing is going to happen in this joint 4 5 6. 4 is axial, 5 is vertical, and 6 is rotation. And same thing 7 8 9. 7 is vertical axial, 8 is vertical, and 9 is axial. So we can see we can use this stiffness matrix. We can see 1 2 3 4 5 and founding this below. Okay, after calculating, and then we can founding this all data. Okay, now see here another the stiffness matrix method for 2D frame for neglecting axial deformation. Okay, so now we can neglect the axial deformation. We use the stiffness matrix for neglect the axial deformation to calculate the point A. This is the point A, and also rotation displacement point B. This is the B point B, and draw the SFT unity diagram. So as S of X is neglected in given in the question, and S1 we have been found 12 pi by L, S2 is 6 L square, and S3 S4 L square, and S4 equal to 2 L square. This is the formula, and finding this below. Now we have been solving this equation as in this case. So let's see here. The axial deformation neglect the problem neglect in the problem shown figure, and displacement U4 and U4 are 0, and the unknown displacement U3 and U6 in this case, that the modified equilibrium equation is given here. So let's solve this problem. So case 1 or we can say case 0, the fixed in moment of reaction. This is the fixed in moment reaction. Case 1 you can say reaction due to U3. This is the U1 U2 U4 U5 U7 U8. This is the U3 for rotation, so U3. And the case 2 is reaction due to E6. This is the U6, so case 6. Okay, so let's solve. As these are the point load from this member, we can use PL by 8 and founding 12.5. Okay, and the same thing we've been shown here as the UDL loop 12 WL square by 12 and founding 8.33. This is the 8.33 and this is the 8.33 anti-clockwise. Okay, I will get this is the 10, so it will be half 5, and it will be also 5, so that's why I have 5 and 5. If this is 5, and okay, let's see the U3 means this is the rotation F3, and the S3 will be the sagging point of the U3, and U3 and U2 will be on the opposite direction. And the same thing, the opposite point will be shown here. S4 and S2 will be opposite direction. Okay, and another one we can see U3, that means rotation will be taken the rotation with respect to this point. So at first this point, then it will be sagging will be like this, and if the load is rotating here, the sagging will be like this. And when the sagging on the sagging will be like this, then the midpoint will be S3 and opposite direction will be S2 and the opposite point is S4, and the opposite point is S2 also. This is the vice versa direction. Is S4 is here, then S2. Okay, Now we can calculate the moment at point A. This is the point A. We're taking the diagram on friction moment will be found here. uh, 12.5, this is the 12.5, and S3, this is the S3 at this point, and U3, this is the U3, and S4, this is the point of this point, this is the we are calculating A point, that's why S4 into U6, S4 into U6. Now we are putting this below as S3, S1, S2, as we have been solving here, S1, S2, S3, just putting 10 into 10 to the power 6 and this below and finding here, and we're just taking the equation is here. This is the value we have been calculating here, S2, S3, S4. This is the calculating here. We just putting this value S3 and S4. The main thing is happen in MZB. This is the MZ and point B. Where is point B? This is the point B. Okay. So taking first moment is 12.5. This is the moment it is shown 12.5. As anti-clockwise, this it is minus 8.33. So if I change here, now we are calculating point B 12.55. This is the 12.55 and 8.33. 8.33 is another moment, and S4 into U3, this is the U3, and S4 is given here point B, as we are calculating point B all over the here S3 and S3 plus UL, this is the S3 and another S3 is here, and into U6. Now we have been finding 1 and 2 after solving there this, then we've been found U363. Okay. The calculation of internal forces, shear force, bending moment, shows shear force. So we will take the shear force A, that means the vertical point at point A. So vertical point A, if I change the color, so it will be 5 and S2 and S2. Okay, so 5 S2 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 is 2 into 3, S2 into 3, and putting this below and form, and every in the similarly we can calculate all things, and bending moment we can also calculate this way. You can see another example. Use the stiffness practice method, neglect the deformation to calculate the reaction at point Y. This is the point of Y. And the displacement is Z. This is the Z, and from ABCD, and rotation figure. So this is our main diagram for the due to lack of the spacing. That's why I'm here. I'm just drawing like this way. So first of all, we've been shown here friction moment is here, as this is the and BZ, that means shear, and UZ, that means rotation at here. So friction moment we've been found here as UDL WL square by 12 and founding 9. BZ is 1 is applied, S1 is applied at joint in upward, then S2 will be downward. The same things, it will be opposite direction, S2 and S1. And UZ, theta, we have been taking the rotation at point Z. That's why this member will be act this like, and this member will be act and deflected like, and this member will be deflected like this. Okay. Now we can see here, we are just putting all this S1. There is no S1, S2, S3, S4. We are just all putting below and forming here below. Summation of moment My. So we are taking the moment of Y this way. So putting this below and funding this diagram also. Uh, so stiffness matrix in the same things. This is our main diagram. Uh, we have to calculate the rotation at y. This is the y and z, and this is the z. So this is the 15 moment, and this is the u1 in this point. This one we are taking the rotation and another rotation taking here, and the member deflection is shown here, and calculating all this here s1 s2, but ex is not needed. S1 s2 s3, s1 is 12 by l cube, s2 is 6 by l cube, and s3 4 by l, and s4 equal to 2 by l, and funding this equation at this value. Now in the same way we just taking the moment my. So this is the y. The y point, we are just summarizing all the moment at point y. 2 into s yb. So this is the moment. We are taking the moment to s3 into yb. So you can see this s3 and this s3 the same, and z3, this is the z3. We just change the name is z3. For u6, this is the u6, and another one u4, s4 into 1.5. This is the s4, z4, you can say s4 into 1.5, and 15 moment has been found as 117. And in the same way z, z means this point, and we're taking all this point and finding this value and moment. Share this area and moment diagram only like this. So this is our diagram, as there is no support, so we are just taking 5 into 10, which is 50. Now this is the only diagram, so we can use this diagram equal to s3. So we are taking the rotation is here, and bz is upward, and friction moment, and we have been taking s2, s3, and we are taking the moment mz. This is the z point, and s3 into theta z. So s3 into theta z, and 33.133, which is 15 moment, and 50 we've been shown here. This is the 50 is given in question. After calculating this, then we can find the theta z. The same way, if we calculate my, then found bz like this way. Okay, so if when the support z is settled, then we can calculation this way. Okay, if the diagram is showing like this is the complex, so we are just putting we are just dividing this section is like this, as we have been shown. This is the internal hinge, so we are cutting here 5 into 5, this is the 25. And after this finding, and then we can use this value theta z, and del y. This is the del y, this is the y, and this is the z, and 15 moment, PL by 8 or W square by 12, whatever. It depends on the load. Then we can use S1, S2, S3, or Y1, Y2, Y3, just changing the name, and the calculation will remain same. So we know here S3 into theta z, so theta z into S3 here, and S4 equal to Y or U4, where S4 equal to theta y, and 12.5, which is 16 moment. This is the 12.5 and 25, and this is the equation, and my also taking this and finding equation 2. After solving equation 1 and 2 and finding this value for bending moment, another one S3 theta z, S4 theta y, and 12.5, and finding, and this is the diagram. Okay. So if the diagram is like this, then we can detect this and rearrange the diagram here. If the diagram is here, then we can reduce after the hinge point. So we are just deducting hinge point and final diagram will be like this. Okay, let's see another example here. This is the diagram we've been shown here. The case 1 theta c, taking the theta b is here and b also taking the particle here, and 15 moment which is wl square by 8 or 12 s1 s2 s3, or you can see z1 z2 z3. This is the beam and moment is found here shear. When the support B is settled, if the settled is given, then we can calculation here on this value. Okay, so here we can see another example here. For this diagram, we can write this diagram, which is fixed moment wl square by 12, and case 2 we've been taking the rotation at this point. That means this point we're taking the rotation, and another one is a by, which is the vertical displacement here. So s3 is opposite direction. We've been writing s2, s3, s4. S1 is don't need it. So we're taking the moment at z. So this is the z. So z after putting and forming this, and f of y, we can calculating f of y theta z and forming theta, and bending moment diagram we have one also calculating here. Another example we can see, and here this is equal to the 15 moment is 1, that means the rotation is here. Case 2, that means the upward pressure is here. Then s1 s2 s3 s4 theta z, and we've been calculating all this here. This is the formula s1 s2 s3, and mz we can calculate the z, this point z, mz is here. Then we will found the rotation, and the bending moment diagram is here, so it will be like this. Now you can see here another frame, which is A is rotating anti-clockwise 1 degree. We've been shown here. Case 1, this is the 15 moment case 1. Case 2, we've been taking the theta rotation at this point, and case 3 we've been taking the rotation this point, and case 4 we're just applying the vertical load is upward. Okay, now we can see here after funding here, we can see here s3 s4 s3 s4, just we just changing the name. S is for instead of s3, as this is the not same value we've been finding here. Taking the moment point A, this is the point A, this is the point. So we have been taking the four cases from here, and mz in the consequently we've been finding the rotation and found the displacement. Okay, we can see here another last example is determine the internal moment of each support of beam from the given from the beam in given EI is constantly use stiffness matrix. So S1 S2 S3 we know that this equation, and forming this value, and S prime 1 S prime 2 S prime 3 S prime 4 is given here, and holding this value. So for this diagram we can find the fixed moment wl square by 12, and case 2 is theta 3, we have been taking the rotation is here, and another one we have been shown the theta c, we have been taking the rotation is here, and case 3 is here. and the moment and moment A and moment B, moment C have been found in here, moment D also. Solving equation for 1 and 2, this is 1 and this is 2, and finding the rotation B and C respectively. And then we can use the bending moment diagram as calculating as a B bending moment at B, a B in BE, and bending moment B and BC, bending moment C in BCD and CD, and consequently finding this below. After finding this below, we can draw the diagram of bending moment. Okay, thank you everyone. If you have any question, then let me know. uh, Thank you everyone, thank you.